Okay, piggybacking off of the last video I created, we're doing something a little different with these first two, but we had these results. So whether or not you watched it, that's okay. Like I said, we're doing something different. But this third one over here, I wanted to point something out. For one-to-one functions. So basically we had said if I could think of any two x's that would yield the same value, and oftentimes with squares it's really easy. Think of, one positive, one negative value. This function is not one-to-one. And I chose 2, but you could choose 1 or 3 or any fraction decimal, it doesn't matter. So like if I thought, f of 2 would yield me 5 times 2 squared minus 2, so that'd be 5 multiplied by 4 minus 2, which is 18. But f of negative 2 would yield 5 times negative 2 squared minus 2 would yield the same thing, right? Because this is 4. 5 times 4 is 20, minus 2 is 18. However, note that this domain restriction, it's telling me in the problem x is greater or equal to 0. So because of that, this is not in the domain. Like, this doesn't count. I can't do that because that's restricted from the beginning. So if that's the case, there's no other number I could think of to get this 18. Right? If I start at 0 and go all the way to infinity, I would get different outputs for each of those numbers. Again, sometimes thinking analytically, numerically, which is like what I was just saying, thinking of values all the way up to infinity, or graphically, knowing that this is some sort of parabola. Do I know exactly what it is? I mean, I do, but maybe not exactly. But it's a parabola, and it does have its vertex at 0 here when x is 0. But if I wiped out half of it, right, if I'm only looking over here, it is a function, and it is one-to-one now. It would pass the horizontal line test because this side doesn't even count. All right? So I had referenced that before, and that is something that could come up. To find its inverse, we'll do it mentally. It says take x and square it, then multiply by 5, and then subtract 2. So remember, we're doing all of that in reverse. So it says take x and square it, then times by 5, and then subtract 2. Sorry, my handwriting is horrible. So I'm going to do that in reverse. I'd add 2, and then I would divide by 5, and then I would square root it. Okay, that would be my inverse, and you could verify that algebraically as well. Okay. All right, moving forward. Another concept I want to show is, like, how do you know if you get your math right? You can verify that your function, your inverse function, is in fact the inverse by doing compositions. We need to show that if we compose these two, and in fact we'd have to compose them both ways, it's kind of a pain. If you get x, then they are in fact inverses of each other. So what does that mean? Remember, a composition means take this function and substitute it in here, right? It says compose f with its inverse, so take the inverse and substitute it into f. So I'm going to take that cube root at x minus 1/2, and I'm substituting it in for x, which says it's cubed plus 1/2. Then cube and cube root cancel, and I am left with x subtract 1/2 plus 1/2, which is x. Okay, so far so good. But we also need to compose it the other way. So that means take your f, right, and take this and plug it in for x here. I just like to rewrite this. So take your f of x, and I'll go and even rewrite this whole thing, and substitute it into the inverse function. So it says x cubed plus 1/2 minus 1/2. Since it's just x minus 1/2, I didn't need parentheses. And it's all cube rooted. Well, 1/2 minus 1/2 is 0, so we have cube root of cube x, which again is x. Okay, so therefore these are, we were correct in the last video, they are inverses of each other. All right, next what I wanted to talk about was the domain and range here. Because we are changing the x and the y, if you find the domain for f, that'll be the range, right, for the inverse. And vice versa, if you find the range for the inverse, it'll be the domain for f. So if I look at f of x, let's go in and switch colors here. F of x, its domain. The domain has no restrictions, right? It's a cubic. I could substitute any value in there. -infinity to infinity. Well, that means that's also the range for the inverse, right? The domain of f of x is the range for the inverse because I switch in x and the y. I think this is the easiest approach to explain this. If we look at domains for both, so the domain of the inverse, I know will be the range for the original. Then we have them all squared away. So looking at, and it's because domain is much easier. If you have a graph, domain and range is easiest just looking at the graph, but I don't really want to graph both of these. Okay. All right. So the domain for a cube root here, a cube root can be negative, right? A square root cannot, but a cube root can. So that we have no problems again. So the domain of the inverse is all real numbers, so that's the range for the original. Okay, now I have domain and range for both. In this case, it's all reals for everything. In this next example, we'll look where it's actually not. All right, so this graph, I don't want to actually graph it. I'm just saying if you did have the graph, you could tell the domain of 1, is the range for the inverse. Also, even if you have no idea what this graph looks like, we could do a table of values and then just remember to switch them, right, for the inverse. Switch the x and the y. Okay, let's first verify, are these in fact inverses? Maybe my math was incorrect in the last video, but I don't think so. Never know. So substitute the inverse in for this x. Well, there's more than one of them, right? So I need to substitute that into both of those x's. So I have 1 minus x, which is 1 over x plus 1, over another x, 1 over x plus 1. To simplify something ugly with all these fractions, I prefer to just multiply by the LCD, which is x plus 1 over x plus 1, because that's just 1, right? Multiplied by a form of 1. When I distribute, I get 1 times x plus 1 minus 1, because those would cancel. And the denominator, they also cancel. So x plus 1 minus 1 is just x. X over 1 is just x. So far, so good. So now we need to check this. So now take your original function, 1 minus x over x, and substitute that into the inverse. Okay, so the inverse is 1 over x plus 1. But remember, I'm plugging 1 minus x over x in for that x. ugly for a second. These always clean up nice, because if they are in fact correct, we just get x. Again, I don't like all these fractions. I have a fraction over fraction. I'm going to multiply by the LCD, which is x, right? There's only one denominator, it's x. X times 1, x. And then distribute in the denominator. X times all of that, the x's would cancel, and I would just have 1 minus x. And then plus 1 times x is x. Again, x's cancel, negative x plus x, right? So x over 1 is x. Because we got x on both compositions, I know for a fact these two were inverses. Okay, we are good to go. Now let's talk about domain and range. Technically, we're only talking about domain. So we're going to do domain for f of x. We're going to do domain for the inverse. Okay, f of x, right here. X, we cannot divide by 0, right? Which tells me x cannot be 0. That is the only restriction for f of x. Often we want interval notation. I am perfectly fine with you just saying x is not 0. In interval notation though, right? Negative infinity to 0, union 0 to infinity, same thing. And that domain is the same as the range for the inverse, because we changed x and y, right? If we change this domain to this range, then they'll have the same restrictions. Looking at the inverse, 1 over x plus 1, x cannot be negative 1. Negative 1 would make me divide by 0. So therefore the domain is negative infinity to negative 1, negative 1 to infinity, and remember, since that's a domain for the inverse, that's the range for the original function.